Hi, in today's lesson, we'll be talking about calculating rates of change. A relationship between two variables where one, y for example, is a function of another variable such as x. The variable x is often considered to be independent variable, whereas the y is a dependent variable. The value of y depends on the value of x and is found by applying a rule connecting the two variables for the given value of x. Normally, the rule contains what we call the slope or the rate of change. The rate of change is a measure of how two variables are related to one another. The rate of change can be expressed in many ways, and one of the ways it can be expressed is an equation. If we take a look at here, we will see an equation that calculates the slope or the rate of change. If we have data, it looks at the change in y, which is our dependent, over the change in x, which is our independent. So if we had a value like 2, it means that for each time the x changes by 1, the y value will change by 2. So we did mention that the rate of reaction can be expressed in many ways. We can use a table or we can show it in a graph. For the rate of reaction, looking at a graph, we would be again looking at the change in y over the change in x. We'll call this the rise and the run. So this is the change in y and this is the change in x. My bad. So here we would see that for each time our graph increases or goes to the right by 8, our y values would go up by 5 points. And that's the rate of change here. That for each 8 we will move 5 up. Right? Or we can take a look at this. If we're looking at this, we are looking at the x values, which is our independent, and you can see how they give us our y values, which are the dependent. So here we actually have values that we can plug into this equation to say m is equals to, you can choose any 2 points that you want. So we will have here 15 minus, let's see this number clearly, minus 3 over our change in x, which is going to be 6 minus a negative 3. The top will get 18 and here we'll get 9. That minus that, and here we'll have this, that over there minus that over there, giving us 2. So for each one that my x changes by, my y will increase by 2 points. The rate of change can be a linear function, as we have seen in our previous examples. This is where the slope or the rate of change is constant between 2 adjacent points in a straight line. We also have a rate of reaction that is nonlinear. It is normally represented by a graph. So we can see that the rate of change on this graph won't be the same because the slope is continuously changing, so it's not linear. For those that are not linear, we can calculate the average rate of change by still using the quadratic equation. The rate of change can be negative or positive. If the rate of change is positive, it indicates that both variables are either increasing together or decreasing together, though not necessarily at the same rate. So, positive, for example, let's say that you have acceleration, right? So your acceleration could be constant at 1 meter per second squared. What does that mean? It means that your speed is going to increase by 1 meter per second for each second that you travel. If we have a negative rate of change, it will indicate that the variable increases while the other is going to decrease. So say you have something like 2 meters per second squared for your acceleration. It tells you that for each second that you spend, your velocity is going to decrease by 2 meters per second. Here it was increasing by 1 meter per second. Here it is decreasing by 2 meters per second, when this one over here increases by 1 second. So for each second that you spend. The rate of change in a function can be estimated by looking at how steep a graph is. For this question, let's take a look at an example. The graph below shows the United States population from 19th to 2010 as recorded by the USA Census Bureau. So question 15 wants to know what was the rate of change in the population from 19,000 to 2000? Is this greater or less than the rate of change in the population from 2000 to 2010? So let's go from this point over here to 2000, which is that, sorry, that point over there. And we can calculate the average rate of reaction, of growth here by calculating the change in y over the change in x. So in terms of our y, we had a population of 70. Let's start with the one at the top. We had 275 million minus at the bottom, we have 75 million, and we will have a difference of 2,000 and 19,000. Let's plug that into the calculator. And that's going to give us 2 million per year. So the population increased by 2 million per year between 19,000 to 2,000. Let's look at the difference between 2000 and 2010. Our gradient would be in 2000. In 2010, we had 325 million. And in 2000, we had 275 million, and we'll have a difference of 2010 and 2000, giving us, see here, 275 over 2010 minus 2000. As 5 million per year. So clearly, during the year of between 2010 and 2000, the population increased more by 3 million than between the years of 2000 and 19,000, right? Because they only increased by 2 million, where over that short period, they increased by 5 million per year. per year. So the one with the greater rate of change is going to be this one, and this one will be less. Which 10-year time period have the greatest and the lowest rate of variation? How did you find this? It's about looking at the change. So in this 1 year, it looks like we increased by somewhere 20 million. In the next year, oh, that is even lower, something like 25 million. And this year here, a little bit greater. We would say something like 95. Here, oh, that is very small, that's 10. And here we had a growth of over 25, a whole 25. That's a lot. And over here, I think over here is a bit more, maybe 26. Over there, something like 24. Over here, 25. Over there, another 25. Over there, another 25. And over here, 25 and maybe 15 more, so 40. Right. So in this year, for 1 year, we increased by 40 million. So the greatest change will be here. The lowest one, it was somewhere over here. Here it is, just that bit, that piece there. So it's not necessarily, I think it was supposed to have 15 here. If you look, it's somewhere at 95 and it's ending at 5, somewhere at 90, ending at 5. So we can say it's 15. So between 1910 to 1920, we had the lowest growth per year. We had something like 15 to 10 million per year, whereas between 2020, we had 5 for each. Sorry, I meant to say, but between those two there, we have a much greater for each for these 10 years that we have. So this is per 10 year. We had 46, actually 50 if we take a look at the calculations a little bit. 5 instead of per year. So I wrote it as something like 40 because I'm estimating, but just looking at the graph, I wrote it something like 40 million per 10 years. So this is pretty much close to that, but we can see that this now has the largest, and over there, the tiny increase there would have the smallest.